So today we're going to talk about light, and light is important for many reasons. Obviously, we need it to see, but in this day and age, technology utilizes light in a variety of different methods, as we'll get to. So let's just start with the basics. Light is a wave, and in fact, the real name for light is called an electromagnetic wave. Light really is just kind of a slang term for that. And so what we mean by that is it's a transverse type wave. And if you take a look at the animation here, the red represents an electric field. And you have your electric field oscillating up and down. Remember, a transverse wave, the oscillation is perpendicular to the propagation of the wave. So the wave's propagating this way, and then the oscillation of the electric field is up and down. The blue is actually representing the magnetic field. And so you have this alternating electric and magnetic field, both of which are transverse. Now in a future unit we'll get into how that exactly happens, but for now just know that that's what it is. So some characteristics, light is a wave, so we have the similar wave characteristics that we've talked about in the past. So you have the amplitude, for example, which is the height of the wave. This would represent the brightness of the wave. So this would be a dim and a bright wave down here, and this would be a dim wave up here. One thing I did notice is this picture has an error somewhere. So I would like you to figure out what that error is, and then I'll ask you this question tomorrow in class. So this picture, the amplitude picture, there's an error somewhere. Figure it out. So the other main characteristic is the frequency and wavelength of the wave. So recall the wavelength would be the length of when the wave begins to repeat. So if we start right here on this red wave, we would repeat right here. This would be the wavelength. In fact, this red wave would have 1, 2, 3, 4 waves here. Okay. This really tells us, well, for visible light, it tells us what the color is going to be. So red light, for example, has a longer wavelength than, say, purple or violet light. So here you can see the wave is much, much shorter than this red wave. Recall frequency is the number of waves per second. And so if this is a snapshot of a second, then this red wave, as I said, would have 4 waves per second. That would be the frequency, or 4 hertz. Let's see, the violet light would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, I think. I might have miscounted, but anyway, the point is there's more waves per second. Recall that a longer wavelength has a lower frequency and a shorter wavelength has a higher frequency. So where amplitude tells you how bright it is, so notice these would be all the same color, just this would be a brighter wave. These would be the same brightness, they have the same amplitude, but if you looked at these different waves, you would see different colors. So the visible light actually is a very small part of all the different electromagnetic waves that are possible. So this is what we call the spectrum of waves, and I do want you to know all 7 forms of the spectrum. So let's start over actually on the right side, starting with the longest wavelength, which we call radio waves. So this would be a long wavelength, which means a low frequency. There's also the energy of the wave as well, and we're going to get into this in a future unit, but just know that the frequency and the energy are direct relationships. So a low frequency means also a low energy. So radio waves, we use these obviously for radios, but also things like cellular communication, satellites, and so forth. So these have a very long wavelength. But they're low energy, and that's important. That's why we use them. One of the reasons, at least, for communication is just because of the energy. It's not going to be damaging to us. Okay, we move into microwaves. This is going to have a shorter wavelength and a higher frequency. Obviously, your ovens are going to use microwaves. We also use it for communication as well. Infrared. This would be heat, for example. Actually, you right now are giving off invisible infrared light. So even though you can't see it, you're giving this off. And if you had special goggles, night vision goggles, for example, we could see things in the dark based on the infrared that they're giving off. Here's our visible light. We often break that down into the colors. So here's your Roy G. Biv that you probably learned about in elementary school. Okay, and red would be the longest wavelength. Orange, yellow, green, blue, indigo, violet would be the shortest wavelength. Ultraviolet, again, we're moving into higher frequencies, lower wavelengths, shorter wavelengths, and higher energies. So ultraviolet, for example, is what gives you a suntan or sunburn. We're moving into kind of the dangerous territory. X-rays, okay, even higher energies, and then gamma rays would be the highest of them all. Both of these are very dangerous in high doses. So let's look at some of the math. We have our wave equation, if you recall, when we talked about in sound, which is essentially V equals F times wavelength, where wavelength, lambda is the wavelength here. Now, the speed of light is what we'd use here for velocity. And in a vacuum, this is a common number we're going to use a lot. In fact, this is the highest speed known to humans, which would be 3 times 10 to the 8th meters per second. Just to give you some perspective, that would be 186,000 miles per second. So we're talking about extremely high speeds here. In fact, the speed of sound was only 343 meters per second. So this is, 300 million. So much, much, much faster. The symbol we use is C for just in a vacuum. Okay, whatever medium we travel in, the speed is going to change. If you notice from the last slide, it does travel in a vacuum, unlike sound. So it is not, light can travel in a vacuum, empty space. However, when it travels in different mediums, it's going to slow down. And so one of the symbols we use to help us with this is called the index of refraction. You can think of this as like the optical density of material. So the equation that we use here, we'd say V equals C over N, where this is the velocity of light we're looking for. This is 3 times 10 to the 8th. And then N would be the optical density or index of refraction of the material. Notice as the density of the material goes up, as the index goes up, the velocity is going to go down. So the higher the N, the lower the speed. So some common M's that we can look at. Well, for a vacuum, if you look, in a vacuum, N would have to be equal to 1. So then you have V equal to C, right? So that would be 1. Notice in air, it's basically 1. So it's, for all intents and purposes, we're going to say the speed in a vacuum is the same as the speed in air. Okay, and then as we keep increasing the index of refraction, the speed is going to be decreasing in the opposite direction. So let's do a calculation here, and I would like you to go ahead and push pause on the video and see if you can solve this on your own, and then I'll come back and do it with you. So if you don't have your calculator, take it out, push pause, and go ahead and see if you can solve this. All right, I'm back. So let's take a look. First one, we're going to go ahead and use our wave equation, V equals F lambda. The color red here is 650 nanometers, so that represents our wavelength, 650. Now, the conversion for a nanometer is 10 to the negative 9th, so we could just write that as 650 times 10 to the negative 9 meters. And then you just go ahead and do the math. Divide it out, you'll get your frequency, 462 10 to the 14. Remember, a hertz is cycles per second, or waves per second. So I do want you to notice this is a huge, tremendous number. And why is it so big? Why do you think this number is so big? Well, 2 reasons. Number 1 is the speed of light is so fast. So remember, this would be, let's say you're looking at red light. It's telling you you're going to see 10 to the 14 waves every second. That's how many waves are hitting your eye every second if you look at red light. So one of the reasons is the light itself is so fast. And then the second reason is the waves are so small. So that turns into a lot of waves per second. Okay, second part of the question, let's look at in water. We're going to be using our velocity equation with the index, v equals c over n. Okay, so we're going to have 3 times 10 to the 8th divided by 1.33, which is the index in water, and you get 2.26 10 to the 8th. So notice it is slower. Now it's still ridiculously fast, but it does slow down a little bit. So what else changes? Well, when light travels through different media, obviously, as we just said, the velocity is going to slow down. However, the frequency itself is going to stay constant. So that means the number of cycles per second will stay the same, whether you're in air, whether you're in water, whether you're in diamond, anything, the frequency stays constant. So if the velocity goes down, that means that the wavelength will also decrease. You can see in this picture, if you double the index, the velocity would get cut in half, and the wavelength would also get cut in half here. The frequency would stay the same in both cases. So let's do one more example. Actually, this is a continuation of the last example. So again, why don't you push pause, see if you can solve this, and then I'll come back and do it. All right, so recall that we calculated the velocity in the vacuum to be 4.62, 10 to the 14th. Now remember, that's going to be the same in water as well, so that stays constant. So the frequency will stay constant regardless of the medium. The velocity in water, we calculated to be this, 2.26, 10 to the 8th. So finally, we're just going to use our equation again, and we'll just use the velocity for water and the frequency for water. And we should get a wavelength of 4.89 10 to the negative 9th, or 489 nanometers. So notice, just as we predicted, as the velocity decreases, the wavelength is also going to decrease. So 650 down to 489. All right, so I'm gonna go ahead and end that here. We obviously will continue on with light as we move forward, but that's it for now.